The modern world is just awash in information, isn't it? And you, our savvy listener, you're often faced with making sense of, well, huge amounts of it. Think about the last time you had to gather all the details for a big project, or maybe compile a list, checking off specific criteria for some important decision. It can be really tedious work. For a little while now, we've heard this promise about large language models, LLMs, especially those powered by these advanced agentic frameworks. The idea was they'd free us from this repetitive, wide-scale information searching, like having a super efficient research assistant to scour the web, organize everything perfectly.
Yeah, and what's really interesting here is that while these agents can do some incredible things, their actual reliability, their completeness, especially for this broad, large-scale kind of gathering that's been largely unproven, it's one thing to find a single specific fact. It's quite another to collect, say, every single relevant fact from a massive pool of data without any mistakes.
And that specific challenge is what we're diving into today. We're looking at a really interesting new benchmark called WideSearch. It comes from a team at ByteDance Seed. And this isn't about finding that one needle in the haystack. It's about making absolutely sure you've collected every single piece of hay that fits your criteria and that it's all organized just right.
Right. So our goal for you today is to help you understand what this wide information seeking really involves, how this new benchmark actually works, and maybe most importantly, why even the most advanced AI agents right now struggle so much with these tasks. Tasks that, humans find tedious, sure, but ultimately we can manage them.
Okay, so let's unpack that phrase, wide information seeking. We all feel that information overload sometimes. And lots of real-world tasks, think financial analysis, maybe job hunting, they require collecting this huge volume of specific, verifiable details. The source material describes this kind of work as being more repetitive than cognitively complex.
And that really nails the core challenge that WideSearch is designed to address. It's about tasks where the sheer volume of data is the main hurdle, not necessarily how difficult the concepts are. The paper makes a point of contrasting this with other kinds of benchmarks. For example, there's something called deep search. That one focuses on finding very specific, maybe hard to find facts. Sort of the I just can't find it anywhere problem.
Okay. And then they also mentioned deep research.
Yes, and that's different again. Deep research is more about synthesizing complex information, building a narrative, the I can't quite write it well problem, perhaps.
So WideSearch is carving out its own space then.
It is. It's focusing squarely on that I could do this, but wow, the sheer volume is overwhelming problem. It's all about thoroughly and accurately gathering all the required large-scale atomic information, those individual facts that meet certain criteria, and then crucially arranging all of that into a well-organized output. Often that means a structured table.
Okay, so what does that practically mean for you listening? Think about needing to find, say, all the companies in a certain sector that meet specific revenue and growth criteria. Or maybe all the job openings that match a specific role, location, and experience level. Those are wide search tasks. The source calls them excruciatingly tedious for humans. But you'd think, theoretically, they'd be perfect for automation.
That's the assumption, but the benchmark tests that. So to evaluate this systematically, the researchers created WideSearch. It's the first benchmark specifically for these wide context information gathering tasks.
And it sounds pretty robust. They got 200 manually curated questions.
That's right, 100 in English, 100 in Chinese, covering something like 15 different domains. And importantly, these aren't just abstract questions. They're based on real queries that users actually make.
So each task requires the agent to find what they call large-scale atomic information.
Yeah.
Little individual facts.
Little individual facts, yes, that can be objectively checked one by one.
Right.
And then an agent has to arrange all of that into a well-organized output, usually that structured table format we mentioned.
They gave an example in the paper, didn't they, about master's programs?
They did. It was something like, I want to apply for full-time masters in civil engineering starting in 2026. Can you find the minimum GPA requirements for Ivy League schools in the US and Group of 8 universities in Australia? So the agent first has to identify all those relevant universities. That's the entity set identification part, finding the list. And then it has to fill in the specific GPA requirement for each one on that list. That's the attribute filling part, getting the details for every item.
Wow. And building this benchmark sounds like it was a huge undertaking itself.
Oh, definitely. They used a 5-stage quality control pipeline, really rigorous. This was to make sure the tasks were genuinely difficult, that the gold standard answers were complete, and that everything could be verified. Get this. The human annotators who created these gold standard answers spent, on average, about 2.33 hours per task.
2 1/3 hours.
per task, and they consulted around 44 unique web pages on average for each one.
Okay, so it's definitely not just a quick Google search then. That's some deep validation work.
It really is. They needed to ensure these tasks genuinely go beyond what an LLM might just know internally and require actual complex use of search tools and information integration, like building a mini database from scratch perfectly.
Right, so after all that careful setup, the big question, how did the AI agents actually do? They tested quite a few, didn't they?
They did. Over 10 state-of-the-art systems. This included single-agent setups, more complex multi-agent frameworks, and even commercial systems you might recognize.
And the results were? Well, you described them as sobering earlier.
They were quite stark. They found that most systems achieve overall success rates near 0%. Near zero. The absolute best performer only reached a 5.1% success rate.
And that's based on their very strict success rate metric, right?
Yeah, extremely strict. It demands a perfect match to that gold standard table. All the content, the structure, everything. Any single mistake, one missing item, one extra item, one incorrect detail, means the entire task is marked as a failure.
That is tough. How did humans fare on this, did they say?
They did mention that a single human tester, even given enough time, only managed about a 20% success rate in a single try. So these tasks are genuinely difficult, even without the AI aspect.
Still, 20% for a human versus near 0% or 5% for the best AI? That's a huge gap.
It is, although interestingly, the study did find that multi-agent frameworks tended to do better than single-agent models when looking at F1 scores.
F1 scores measure partial correctness, don't they?
They do, so that suggests breaking down the big query into smaller, parallel subtasks, which multi-agent systems often do. That seems to help get more of the individual facts right, but it still doesn't solve that core problem of achieving total completeness and accuracy for the entire table.
So what about the big names? The commercial AI assistants people use every day?
Similar story there. The study looked at leading models like Gemini 2.5 Pro, Claude Sonnet 4, OpenAI o3. When using their built-in web browsing modes, they also hovered around that same 5% success rate mark.
So it seems like a fundamental limitation right now, regardless of the specific system.
That seems to be the case. Which naturally leads to the question, why are they failing so badly on this specific type of task?
Yeah, what's going wrong?
Well, a key finding from the study is that the failure isn't necessarily about finding individual pieces of information. If you look at item-level F1 scores, how accurate they are on single data points, they can actually get up towards 80% if you let the agents have many, many retries.
Okay, so they can find the individual facts, mostly, given enough chances.
Yeah.
So the real problem lies elsewhere.
The real bottleneck seems to be ensuring, and I'm quoting here, absolute completeness and accuracy of each atomic unit of information within a large-scale search. Think about it. If your task involves, say, 100 universities and their GTA requirements, getting 99 universities right but messing up just one, maybe missing it, adding an extra one, or getting the GPA wrong, that single error fails the whole task by WideSearch rules.
Perfection at scale. One slip and you're out.
That's the essence of it. Any single error, extra data, missing data, incorrect data means total task failure.
The paper actually detailed some specific failure modes, these advanced agentic capabilities that were lacking. What were some of those?
Right, they broke it down. One major issue was incomplete query decomposition. For instance, an agent was asked to find top universities for a subject, including their rankings, websites, and application details. It did okay finding the list of universities, but then it just stopped. It never generated the follow-up queries needed to find the websites or application details. It didn't break the main task down into all the necessary substeps.
Didn't think through the whole request. What else?
Another one was a lack of reflection and iterative refinement. This seemed critical. An agent was tasked with finding GDP growth rates for individual sub-Saharan African countries from the World Bank. It performed a broad search first, which returned aggregated regional data, not country-specific data. Now, ideally, it should have reflected on this result and refined its search to ask for specific countries. But instead,
It just gave up.
it gave up. It reported it couldn't find the information rather than iterating on its search strategy. No refinement loop.
Okay, that's a big problem. And there was one about using the evidence found.
Yes, failure in evidence utilization. This one is quite concerning. An agent needed Harvard's civil engineering GPA minimum. It searched, found a page, and correctly extracted a GPA. 3.04 points. Sounds good, right?
Seems okay so far.
But the source web page it pulled that from, it was actually the University of Houston's website, not Harvard's. The agent found a number but failed to properly check the context of that number, where it came from, and what it referred to. It misattributed the evidence.
Wow, okay, that's a critical error. And you mentioned hallucination, too.
Right, knowledge hallucination and factual inconsistency. An agent was asked for entrance fees for U.S. national parks for June 2025, a date in the future. Logically, it couldn't find current definitive fees for a future date, which is correct. No information found. But then specifically for Everglades National Park, instead of saying information not available, it just made up a fee. It stated $15.
Pulled it from its internal knowledge, presumably, but incorrectly applied it.
Or just generated a plausible-sounding number. Either way, it hallucinated a specific fact when it should have reported uncertainty, leading to a factual inconsistency.
And these were the advanced failures. There were basic ones, too.
Oh, yes. Beyond these more complex reasoning failures, agents also failed due to simpler things. Errors in actually using their search tools, tool invocation errors, formatting the output table incorrectly, or just running into context link limits. Basically, sometimes the task was just too big for the agent's working memory to handle all the planning, searching, and result compilation.
It really underscores how incredibly hard these tasks are. Even for humans, as you said. The paper noted the ground truth itself was tough to create.
Absolutely. The researchers emphasized that creating those gold standard answers involved multiple human annotators doing several rounds of repeated searches, revisions, and cross-validations, just to ensure complete accuracy.
It wasn't one person doing one search. It was a team effort with checks and balances.
Which really drives home this idea of perfection at scale. If you have a task with, say, 5,000 individual data points required in the final table, getting 4,999 of them correct, but having just one error still means failure under these strict rules. That's why the benchmark is so demanding, but it's also why it arguably reflects real-world needs in fields like finance or legal research, where that level of precision is often required.
There was also that test time scaling experiment, which I found fascinating, letting the agents try again and again.
Right. They found that if you gave an agent many attempts at the same task, up to 128 retries in their experiment, the item-level F1 score, so its ability to find individual pieces of information, could climb close to 80%. Pretty good, right?
Right. Finding most individual facts seems achievable with enough tries.
But the table-level success rate, getting that entire table perfect, complete, with no errors even after 128 tries, it still stayed below 20%.
Still below the single-attempt human level.
It really highlights the gap. Finding some or even most of the information is one thing. Getting all of it perfectly structured and completely accurate across a large scale, that's an entirely different, much harder challenge for current systems.
So wrapping this up, WideSearch really shines a light on a critical gap, doesn't it?
It certainly does. Current AI agents, even the best ones, are just not yet reliable for this kind of large-scale, high-fidelity information gathering. They don't struggle so much with finding isolated facts, but they really fall down on ensuring comprehensive collection and perfect accuracy across that wide scope.
This deep dive really illustrates that while these LLMs and agent frameworks are incredibly powerful in many ways, the road to truly autonomous, dependable search agents, agents that can handle vast amounts of structured information perfectly, well, that journey is still very much ongoing.
It's quite a testament to the complexity of what our own brains manage almost intuitively, even when these tasks feel incredibly repetitive or tedious to us.
What does the research suggest might be needed for progress here?
The paper hints that future advances will likely need more sophisticated agent architectures. They particularly point towards multi-agent systems. The idea is perhaps systems that can better mimic how humans might collaborate on such a task, dividing the work, searching in parallel, and then cross-validating each other's findings to catch errors.
Interesting. So for you listening, the next time you find yourself embarking on one of these wide-scale information hunts, maybe take a moment. Consider that intricate dance of planning, searching, reflecting, validating, and ensuring absolute comprehensive accuracy. A dance that even today's most advanced AI finds extraordinarily difficult. It really makes you wonder, doesn't it? What kinds of breakthroughs, what new approaches will finally bridge this gap and truly change how we all interact with the world's vast sea of information?